All right, now that we recognize that the velocity of a wave is tied in with the frequency, the number of steps, versus the stride, the length of the wavelength itself, we can calculate some velocities. And if we look here, we can also work velocities backwards. Let's say, for example, we have ourselves a radio station. Let's pick your favorite radio station. Okay, you don't have one. All right, how about 94.1 WYSP, Sports Talk Radio? That's probably very popular with a lot of people out there. So we've got ourselves a radio station, and it has a frequency of 94.1, and the FM dial is in megahertz. So if I say 94.1, what I really mean is times 10 to the 6 hertz. Now, if you think about it, those waves, when they come into the radio in your car or whether you're listening at home, there's 94 million of them coming into the radio per second. So if you think about the number of humpy things coming through, we're talking about a major, like, they're extremely fast. So if you think about them, we've got a lot of steps. All right, now what I'd like to do is figure out what the wavelength is. So I need to know something. So in this formula, I know F. I'm looking for the wavelength. Wouldn't it be nice to know what V is? Well, when I'm talking about radio waves, light waves, infrared, X-ray, gamma, microwave waves, those are called electromagnetic waves. Now those are transverse waves, but there's an electro part and there is a magnetic part, electromagnetic. So let's say we'll pick a plane. If we look, the electro part is a transverse wave that's going in this plane up and down like a snake. The magnetic wave simultaneously is also a transverse wave, but it's going in the perpendicular plane like this, side to side, back and forth. So an electromagnetic wave is actually two transverse waves. So when I'm listening to the radio, the wave actually has two components to it, a vertical component and a horizontal. So if we try to do these simultaneously, it's not easy. So I'll ask you to try in class. So when I start out, one goes up, one goes out, then they cross again, then one goes down, one goes this way, and then back up like this, and then we continue that pattern back and forth like so. Not easy to do, two different motions with two different hands. All right, now, the good news about all electromagnetic waves, they all travel at the speed of light, which is 3 times 10 to the 8th. So we already have a bit of information here. The velocity of light is 3 times 10 to the 8th. That includes radio waves, the ones that we're looking for, meters per second. As a matter of fact, this velocity is so popular, it's given its own little letter. So the velocity of light, and you've seen this in formulas such as E equals mc squared. The c actually is the velocity of light, and it's so popular, they actually gave it its own letter, the letter C. Why? Don't ask me. Who knows? All right, so let's go back to our formula. So we know the velocity is equal to the frequency times the wavelength. So in this particular case, we're looking for the wavelength here. So the wavelength is going to be equal to the speed of light divided by the frequency. So if we put that in here, we've got ourselves 3 times 10 to the 8th meters per second divided by a frequency of 94.1 times 10 to the 6th hertz. And if we go back and calculate that, we can actually figure out the wavelength. Well, I just happen to have my Inspire here, fully charged and ready to go. So when I plug in the numbers, we've got 3 times 10 to the 8th. I'm going to use the EE button, so what the heck. And then divide by 94.1, and then that's to the 6th. Okay, so there we go. And I end up with an answer of, whoa, 3.2 meters. All right, and I really do believe that's true. So 3.2 meters. So I'll ask you to describe the waves from this particular station coming into your radio. There's 94 plus million of the little buggers coming into the car at any given second. All right, and the waves themselves, if I asked you to take your hands and then show me the wavelength, what's the spacing between the top of the wave and the next one coming in? 3.2 meters, you would be hard pressed to do that with your arms. All right, so if I'm looking here, 3.2 meters is about 9+ feet, maybe almost 10 feet. All right, so the waves are fairly spaced apart, and they're coming into that car like gangbusters. All right, so that's a typical one for an FM radio station. Now, we could do that with a variety of frequencies and wavelengths, but the bottom line is here, to keep that value for light at 3 times 10 to the 8th, the number of steps and the stride, when you multiply them together, it has to come out to 3 times 10 to the 8th. So if the frequency goes up, that must mean that the wavelength goes down. If the frequency goes down, that means the length of the stride has to go up. So all of these things go to create waves of different frequencies and wavelengths. And we get that broad spectrum. The one constant is how fast the electromagnetic waves travel. Now, let's suppose, for example, I go to the beach. Well, do they travel at the speed of light? And of course they do not. So be careful. This idea right here is only good when we're talking about electromagnetic waves. Now, do ocean waves travel with a velocity v with a certain frequency and wavelength? And they certainly do. So they still obey this generalized law, but if I want to figure out the velocity of those waves, I need to know how frequently they're hitting the beach, I need to know what their spacing is, and I can now determine what that is. All right, now, there are a couple other situations. What about the velocity of sound? And sound is a longitudinal wave, but it still does obey the formula v is equal to f lambda. All right, now, in general, the velocity of sound is given by a formula. It's 331 meters per second plus 0.6 times the temperature. And the temperature is in centigrade. All right, so if we're going to calculate, let's say, the velocity of light, let's suppose the temperature is 10 degrees centigrade. So we would take 331 meters per second plus 0.6 times the 10 degrees centigrade. And then if we add those up, 0.6 times 10 is 6. The velocity at that temperature for sound is 337 meters per second. All right, now note something. As the temperature increases, the velocity of sound actually increases. So on a warm day, the velocity of sound is slightly higher than on a cold day. Now, if I thought about why that would be, let's go back to our example with the slinky. So when the sound comes out of my mouth, I've created a longitudinal or compression wave. So the air molecules bounce off each other and then bounce to the next ones and to the next ones to the next ones until that compressional wave has worked its way all the way over to your ear. I always think about it like the Pony Express riders. So when they went to deliver the mail for the Pony Express, they would take the mail, ride on a horse as fast as they possibly can until they got to the next one. Hand in the bag, and then the Pony Express guy, the second one, would run like this and then go to the next one. And then the third one, and they would continue that until it eventually got to its journey. So I think about the sound waves. We are talking about gas molecules. So when I speak and it comes out of my mouth, those molecules are moving at a certain speed. Now, if the speed is fast, if the horse is driving fast, isn't that going to arrive quicker than if it's cold and the things are running slow? So the faster or the higher the temperature, the faster the molecules are moving, so therefore the message will arrive sooner. So the velocity of sound does the same thing. The higher the temperature, the faster the molecules of air are moving, therefore the velocity is going to increase. So we have this very, very nice formula. Now, there's some other situations as well. Let's say I ask you, what's the velocity of a wave as it travels along a guitar string? So there's a nice little formula for that situation. So the velocity of the wave as it travels, when I go doing, and the sound is transmitted through the spring, through the guitar string, and it vibrates and makes a nice sound. Beautiful, all right? So the question is, well, how fast does it actually travel through a substance like that? So if we look at that, there's a couple factors. All right, now, one of the first things we have to worry about is the tension. So when I'm playing guitar, or if I tune a guitar, on the end of the guitar, at the very end, there's knobs, and those are the tensioner knobs. So we adjust those and then turn them so that we get the right pitch, the right frequency, the right sound. by controlling this velocity. So as I turn the knobs on the guitar and change the tension, that changes the velocity of the wave. Think of that. If the string is tight, when you go to pluck it, doesn't it go ding and it really goes fast? If I back off on the tension and make it real sloppy, isn't the wave just going to take its sweet old time? So there's a direct relationship between the tension in the string and the velocity. The tighter I make the string, the faster the velocity is as it travels along that string. All right, now, another thing to consider is this. All right, on a guitar, there's more than one string. They're not all identical to each other. So when I go to play the guitar and I go to pluck that string, aren't some of them real thick and heavy? And then other strings that play the higher pitched notes are kind of skinny. All right, now, when I think about that, the idea that the strings are heavier or thinner, all right, goes along with an idea called density. All right, now, traditionally, density we think about as being the mass divided by the volume. But when I'm talking about a guitar string or something that's long and skinny, I don't really care about the volume. What I really care more about is how long it is. So when I go to calculate the density of a guitar string, I take the mass and I divide it by its length. So what I would do is this. I would go to the guitar store and I'd say, hey, what's the density of that string that I need for my guitar? So I would take it, and he'd take me over there, and the strings usually come in these little packages. I take the string out of the package like so. All right, now, to make it a fair contest, if I'm comparing the density of one string to another, shouldn't I take the strings and cut them so that they're the right same length? So I take the strings out of the package, set them down on the counter, and I go, da-cha! And I chop the strings so that each string is, say, 1 meter long. Then, once I take that string, roll it up again, put it on the masser, and weigh it, can I figure out what the mass is for the length of, say, 1 meter? All right, now, I go to check the next string. So I go in, I get the real skinny one, you know. So what do? I take it out of its package. Yep, it's all rolled up. Put it all straight like that to make it a fair contest. What do I have to do? I chop the string 1 meter just like I did the first one. Take it back off, roll it up, put it on the masser, figure out what its mass is for that particular length. Now I can actually determine what the density is, the mass per the length of the string. All right, now, let's think about it. If the density is really heavy, let's say that string that has like the curlies on it, if that's real heavy, what's it going to act like? What's it going to feel like when you go to pluck it? Aren't big things heavy? Don't they have inertia? They don't want to move. So that real thick string, the one with a real high density, that one is sluggish. So when the density is high, the velocity is low. So the thick string is going to be slow. They are inverses to each other. Now, that little skinny string, the second one that I cut, all right, it's got a very low density. So the density is low, the velocity is high. So if I'm thinking about it, the density is opposite. So when I go to write the formula like here, I'm going to write the density in the bottom right here because it belongs in the denominator. Now, when I circle this, I like to think about this density, the mass divided by its length, as a thing. That is the actual thing itself. So don't split these up or anything. They kind of belong together, the mass of the string divided by its length. Now, one last thing, because it has to do with the energy of the spring, if we're looking here, we can put a square root sign, and we can now determine what the velocity is of a string on a guitar by measuring the tension and adjusting the tensioners and figuring out how heavy the string is. What I mean by that is the linear density, and then take the square root after we divide them, and that'll actually tell us the velocity on the string. All right, now, this also applies to anything like that. It could be anything that's real long and skinny. It could be a pipe, whatever that material happens to be.